Hello everyone, this is the Chapter 9 video, which is all about weather. Now, some of you might be thinking, why do we have so much to worry about with weather? Didn't we worry about that a little bit when we were doing our private pilot work? The answer is yes. Why do we worry about weather more as instrument pilots? Well, because when you're a VFR only pilot, weather's pretty simple. It's usually a go, no go. Well, if you're IFR, now there's a little bit more to think about. You might be able to make it okay, and maybe you have to worry about ice, maybe you have to worry about storms, things get a little bit more iffy. Also, if you're an instrument rated pilot, you might be taking longer trips. So now the weather can change significantly from place to place. So there are a couple of reasons why you might have to worry about weather a little bit more as an instrument rated pilot than you would as a VFR only pilot. Alright, so I'm not going to cover everything from this chapter. It's a pretty large chapter, but just a couple of the basics. All the weather that we get comes from the sun. So the sun heats the earth, and it heats the earth uneven. So it's this uneven heating of the earth's surface. We all know that hot air rises, and then this air starts to move and circulate in different patterns because it doesn't just go straight up, because the earth is rotating, and there are things that will cap the weather, the air, from going up into outer space and things like that too. So that is the most basic thing you can say about the weather. All weather comes from the sun. So this uneven heating causes pretty much all the weather that we get. Rod talks about the different phases of water. We have water that's in vapor, water that's liquid, water that's frozen, also known as ice. And of course we have things like sublimation. It's a nice fun word that you probably learned in science class in school. It just means you have something like water that goes straight from a solid to a gas or a vacuum. So your snowman, some of the water in your snowman can actually go directly to gas, or vapor in this case. When we look at air, we talk a lot about moisture in the air. So as a reminder, air that is warmer can hold more moisture. In the summertime, you can have those hot, nasty, humid days. And why is that? Because what is warmer? What does that mean? Warmer means that there's more space between all those molecules in the air, right? They're banging around faster, and they're further apart. That's what it means to have a higher temperature. When you have a colder temperature, all those things are kind of closer together, and they're not moving near as much. So you don't have as much space for water. And that's one of the reasons why, as you cool air, you can get the water coming out, right? You get condensation on your bottle. On a hot day, you have a nice cold beverage, and you get water on the bottle, because that air gets cooled, gets saturated, and boom, visible moisture. So when it comes to cooling air, there's two basic ways. You can pass it over something cold. I'll just say a cold thing. It could be a land mass, a cold air mass. There's a lot of different things you can do. Or you can raise it. Generally speaking, as you go up, the temperatures go down. So you can cool something by lifting it up. And these are two different ways to cool an air mass. And again, what happens to air when you cool it? It can't hold as much moisture. So the moisture starts to come out, starts to condense. You can get clouds, you can get precipitation. Now, one of the things Rod mentions is we have something we call the standard atmospheric lapse rate. So the standard lapse rate is 3.5 degrees Fahrenheit, or 2 degrees Celsius per 1,000 feet. That's the standard lapse rate. That doesn't mean that's what the lapse rate is going to be, but that is the thing that we use for calculation. So we can use that for things like this. We say if the temperature dew point spread is less than a couple of degrees, you might expect low clouds. All right, so let's say the temperature dew point spread is within 2 degrees Celsius. What does that mean? Well, what it could mean is you're going to have a cloud layer below 1,000 feet, which means you could have instrument weather. So that's one thing you can take away using the standard lapse rate. Again, it's just a standard, doesn't mean that that's the actual lapse rate that you're going to encounter in any given situation. In fact, one of the next things that Rod talks about are temperature inversions. So what's a temperature inversion? As you go up, things get warmer. Now there are two kinds of temperature inversions you can have. We have inversions aloft, and those are generally speaking caused by warmer air moving horizontally over colder air. Right? So if I have cold air, this cold air, and then I have warm air moving over it. Right? So that air is going to give me higher temperatures aloft. So it's going to be cold, and it's going to get colder, and then it's going to get warm, and then it's going to get colder again as you go up and up. So this warm air will eventually cool as well as it goes up. So that's an inversion aloft. We can also get inversions that are low level, and what does that mean? It's just closer to the ground. And that's a pretty common thing. You know, you have things like a desert. You've got air that's being heated right above the desert surface. You know, what does that do? Your book talks about all those different scenarios. So what should you expect with an inversion? Clouds, cloud formation. First thing you'll expect, bad vis below it. Things are getting trapped, so all the crud is getting trapped in the air, if you will. Low level wind shear, not a great thing if you're an instrument pilot or actually any pilot. And other things inversions tell you is that there is stable air. It's the stable air that's capping things below it. So these are all things you should expect with an inversion. All right. Then Rod talks a little bit about highs and lows. You know, what should you expect from high pressure and low pressure? You know, if I have a high pressure area here and a low pressure area here, you know, I can draw my isobars. Isobars are constant pressure circles. And if I look at some of my charts, I might see something looks kind of like this. And the closer together these lines are, the higher the pressure gradient is, if you will. And then over here, I've got some similar isobars. Okay, so normally I would think high pressure, low pressure, all of my air is going to go straight across. And near the surface, that's pretty much true, right? So near the surface, I've got my wind going from high to low pressure, but aloft, it doesn't go straight there. Instead, it's going to go around these isobars because of the Coriolis effect. Now remember, that what's the Coriolis effect? It is the effect of the Earth spinning, if you will, underneath the air. Why is this more pronounced at altitude? Because you don't have friction with the Earth's surface. So because of the Coriolis effect, the highs, the wind, especially aloft, again, closer to the ground, it goes pretty much straight from high to low, will start to spin. And over here, it's going to spin the opposite direction. So it's going to go this way. So what does that mean to me as a pilot? Now, a lot of people say, if I'm flying, you know, from here to here, I want to be careful about how I go. And, you know, I can take this kind of a crazy path. I can go here, here, and kind of get slingshotted, if you will. How long is your path? How long is your flight supposed to be if that's actually going to work for you? I think that's a legit question. Now, when you look at highs and lows, generally speaking, highs are associated with good weather. Lows are associated with crappy weather. So when you're flying toward a low, you can think of the rule of L. Left, lousy, low. What does that mean? If I'm flying along here and increasingly the winds are going up and getting stronger and stronger from my left, I'm flying toward a low pressure area. So don't fly that way unless you want to deal with some bad weather at least. That's what you should remember. And you probably remember that from private pilot ground school. So high pressure, clear skies, possibly unstable air, but clear skies, lows, bad weather in general. Then we talk about things like troughs and ridges. So if you have low pressure, an elongated area of low pressure, we call that a trough. And if we have an elongated area of high pressure, we call that a ridge. All right. Then from there, Rod talks about fronts. So what is a front? It's when air masses collide. That's a front. So a frontal system is just where you have two different air masses that are coming together. Now, what kind of fronts can you have? Well, there's a couple of different kinds. You can have warm fronts and you can have cold fronts. You can have fast-moving fronts and slow-moving fronts. And then you can have included fronts. Okay, so what should you know about your cold fronts in particular? So a cold front looks kind of like this. And this is figure 58. So I have this nice cold, dense air. It's going this way. What happens? It's going to encounter warm air. This warm air is going to get forced up. It's going to go upslope of this cold front. As it goes up, it gets cooled. What happens as it cools? Things condense. I get clouds. So now I get clouds that are starting to form. If I'm real unlucky, some of these clouds will develop into things like thunderstorms. So that is the very basics of a cold front, a slow-moving cold front. Now what if this cold front is going a little bit faster? In a sense, I can get almost what we call ripple effects. So it's not just right here at the interface anymore. Now, as the warm air approaches, this is coming so quickly, I'm getting essentially ripples or waves almost in my warm air. So now I don't just have this activity right at the front, but I can have activity out here. And this is called a squall line. And if you remember, squall line thunderstorms can be some of the nastier ones. So this is not great if that happens. Okay, quick review on thunderstorms. Thunderstorms are a big problem for instrument pilots and of course VFR pilots as well. But as I said before, you're more likely to encounter thunderstorms as an instrument pilot because you're going to go out on those days a little bit more iffy than you would have flown as a VFR only pilot. So when we look at a thunderstorms, we have our different stages. We have the cumulus, and the cumulus stage, sometimes called the building stage. This is characterized by updrafts. So if I fly through a building cumulus, I'm going to have some nasty updrafts. I might not even be able to keep myself down. You might say, well, that's better than going down and not being able to go up. Some truth to that. However, depending on what's going on, I might get pushed way up to, bad altitudes, like where I need oxygen, or maybe there's some freezing going on at those higher altitudes. So it's still not exactly desirable. And then we have our mature stage. So our mature stage is where we're starting to have updrafts and downdrafts. So what's going on in our thunderstorm now? Well, now we have kind of this churning. So now as I'm flying through this thunderstorm, I can be going up and now I'm going down. Now I'm going up and I'm going down. So it's kind of a dangerous place to be. Pilots have a tendency to over-control, and that's usually what kills your aircraft. It's usually not the turbulence. Although, of course, in thunderstorms you can get nasty things like hail and other things going on in there. So, yeah, and it's not just the pilots, but the pilots are often a big problem when they fly into stuff like that. And then we have dissipating. What does dissipating mean? It's pretty much all downdraft. How do you know when you've reached the mature stage? You start to see precipitation. Dissipating, well, it starts to rain itself out. What are some of the different kinds of thunderstorms you can get? Of course, thunderstorms from fronts, squall lines, we talked about that just a bit ago. So there's a lot of different situations where you can get a thunderstorm. Other things associated with thunderstorms: turbulence, possibly hail, lightning. Obviously, if lightning hits your aircraft, that's really bad, especially for your avionics and maybe for your underwear. Microbursts. Microbursts are localized downdrafts. So if you have a microburst hitting the ground, let's just say here's your storm, and you've got things hitting the ground and then spreading out. If you fly through this, it can be very bad. Some years ago, I was at an airport that got hit by a microburst, and it took out a couple of rows of hangars. I was actually 100 feet from where this happened. An entire row of hangars was destroyed. There were airplanes that were flung into a next row of hangars, and there were some that were actually flung over a row of hangars into a third row of hangars that was quite a distance away. It was a very tragic but impressive thing to witness firsthand. So microbursts can be pretty dangerous. You know, typically don't last very long, maybe 10 minutes or so. Rod also talks about things like wind shear and turbulence. It's the same as when you were doing VFR stuff. You know, what causes wind shear and turbulence? Wind shear just means change in direction or velocity. Wind, it's normal as you go up on certain days where the winds aloft are strong. As you go up, things change direction because of Coriolis force, and they change intensity. So you might get some strong wind shears. You can get wind shear and turbulence near the ground from things such as structural turbulence, where the wind whips around structures, some of them man-made, some of them natural. You have things such as mountain waves. You get those winds that go over a mountain, and they cause some pretty nasty things to happen. If the winds are strong again, you know, here in Bloomsburg, on a strong wind day, you're usually stuck using runway 27. You're coming over that ridge, and I'll tell people, try to hit that ridge straight up. That way you don't get whacked quite as bad with the turbulence. Rod talks a lot about fog. What's fog? It's just low clouds. Clouds on the ground, essentially. How do you get it? Well, how do you get any cloud? You either add moisture or you cool the air till it's saturated. Do either of those things or both, I suppose, and you're going to get fog. I already told you about my story coming in Fulton County one night where suddenly, boom, there was some fog on the ground. So depending where you are and the time of year, this is something that happens pretty quickly, and it's not good, right? Ultimately, at the end of that instrument approach, we need to have some visibility in order to land. So fog is kind of a hazard for us. I'm not going to go through all the different kinds of fog. You know, I always thought it was kind of silly to quiz people on, you know, what kind of fog is this? What kind of fog is that? As long as you understand what causes fog and where you might find it, who cares what it's called? It's called fog. You can't look at that fog and say, well, this is this kind of fog. It's just fog. I can't see through it, and that's all I care about. So again, how do you get fog? You cool the air till it's saturated, or you can add water. Either of those are going to cause fog. Other things we worry about as instrument pilots. Icing. How do you get icing? Visible moisture, which usually means a cloud, aircraft, surface, at or below freezing. That's how you get ice. I say usually that involves flying through a cloud when we say visible moisture, one exception to that is freezing rain. You have water coming from above. Maybe there's a temperature inversion. So things are liquid up top and rains down on you and it freezes. I've flown in icing conditions a couple of times. Thankfully in an aircraft with de-ice equipment. But I'll be honest, even if you have an aircraft that is rated for known icing, don't seek out the ice. It's not a good thing. Even when I was flying my Malibu, you know, some days I can remember you start to pick up ice, and if you don't notice it right away, you maybe don't start using the boots right away. And if ice starts to accumulate behind the boots, well, there's not much you can do to get rid of that. If you're in an airplane that doesn't have de-ice equipment, that's really bad, because now what are you going to do? If you start to pick up some ice, you can try to climb, you can try to descend. There are different schools of thought, by the way, on which way you should go. My instructor said, always go up. If you're getting icing, it might be from something like a temperature inversion. It's possibly warmer up top. So I guess that's one thought. Another thought is that you can always go down, but you can't always go up. So if you start to pick up a significant amount of ice, you might not be able to climb. So the thought is, why don't you try to climb out of it? You know, also, even if it's colder up top and things that are hitting your aircraft, if it's already frozen, it's already frozen. It's not going to necessarily stick to your aircraft. So that's another thing. So when you look at ice, you've got clear ice, rime ice, and mixed. What's the difference? Really, the difference is how quickly does it freeze. Freezes quickly, that's where you get rime ice. It's cloudy. You can think of it as it's got some trapped air in it, however you want to think about that. Clear ice tends to kind of roll back on the surfaces and slowly freeze. And then there's a mixture of ice. Again, don't be crazy. Don't say, well, you know, my aircraft is certified into known icing conditions. Right? Don't seek it out. I remember one time I was actually flying in an airliner. It was a Embraer 145, I believe. And we were coming into, I forget what airport, and I was sitting by the wing in the window seat. And I saw, we just flew through something, and I was just amazed. That airliner, I just saw instantly a sheet of ice appear on that wing outside. And it was kind of crazy. And we were on our final approach into our destination, and I remember looking out at that going, wow. And I was watching it to see if that ice was going to melt. And honestly, that ice didn't even melt by the time we had landed. In fact, I want to say it was the last flight of the day, and we actually sat at the gate for a while they ran the de-ice gear to make sure that, you know, they didn't want to park the plane overnight with a sheet of ice on it. So they're running, you know, all of the wing heaters, if you will. You know, basically they're putting the bleed air out and running the engines to try to get rid of that ice for several minutes after we parked, before they finally shut it down and let us all get out. So icing is something to worry about. So, you know, instrument pilots, what do we worry about? Thunderstorms, we definitely worry about. Icing, we worry about. Clouds, not so much. You know, turbulence, yeah, nobody loves turbulence. But, you know, some parts of this country during the winter time, you're barely going to fly because of concerns for icing. Right? That freezing level is down toward the ground. That's not great. If it's right at the altitude you want to fly, also not great. A high freezing level is not so bad, right? Because you're like, okay, that's fine. I just won't go that high. I won't be passing through that region where icing is going to be a problem. So those are just a few highlights from Chapter 9, which is all about instrument weather. Again, hopefully you guys are enjoying these videos in this class. We're actually about halfway there now. It's chapter 9. There's 17 chapters in this book. So this is the stuff for week 3 of our 6-week class. So I will see you guys around.